Because the mechanism is how you get from point A to point B. But the synthesis is what transformation happens from point A to point B. So this is what we call a multi-step synthesis. First step was to reduce the alkyne down to the alkene. And then the second step was to do oxymercuration on the alkene to give you the alcohol. All right, and then let me change this too. All right, so the multi-step synthesis part, anytime you do a multi-step synthesis, whatever the product is from one step, that's going to become the start material for the following step.
And how'd you say it was different from the multi-step reaction?
No, it's not a, so the mechanism is what happens within a step, right?
Okay, yes.
So it's something like, it's my way of showing, it's my depiction of how I got from within a particular reaction, how I got from start materials to products. But in a multi-step synthesis, every step has its own mechanism, right? So it's not like a stepwise, it's not, I just don't want you to confuse it and say, oh, it's a stepwise. It's you would consider it stepwise still, but it's not just a mechanism, it's the overall formation of a product from one start material, but you do it in use multiple reactions to carry it out. So the product from one reaction becomes the starting material for the next reaction. So when you see it written like this with these three different reactions, each one of those reactions is going to give you something different. But after that first reaction, you no longer have your original start material. You got whatever the product of that reaction is. And then it's that product that gets worked on by whatever the next step in that sequence is. Are y'all following that? Does that make sense?
Yes.
Yes.
All right. So let's go back and put in the product for B, which looks like this. I'm just going to write it in like that. All right, so that's B. We took that triple bond. Initially, we did a substitution reaction to get A, and then we used A to get B, because A, again, in a multi-step process, the product of one reaction is the start material for the next reaction. So A is the start material for the synthesis of B. Any questions about that? All right, now the last reaction is looking at going from D to E. What kind of reaction is that?
Ozonolysis?
It's ozonolysis, good. So what you see with these triple bonds, in an indirect way, what I'm trying to show you is that you can, with the functionality being as it is, you can take that triple bond and turn it into some other functional group, and then use a reaction that we've already talked about, right? So if I turn that triple bond into an alkene, any of the reactions of alkenes that we've looked at, we can apply it. So the question now for E is, what is the product? What does the product look like?
Are you gonna have some type of chain where the aromatics are?
No.
No.
Oh, good question. Good question. So the aromatics, even though they have pi bonds in the ring, the aromatic ring is very stable. Like you're not going to break those pi bonds. It's only going to be, that's a great question. It's only going to be this pi bond right here that gets acted on. So the aromatics are too stable to undergo ozonolysis. You can't break that ring. You can't pop that open. You can't pop it open with a sledgehammer.
Okay, so it's not like the other, I guess the other one where
Yeah, it's a special class of alkene because there's a couple of reasons why it's so stable. First of all, it's like it's what we call conjugated, where you can see a pattern of like you got a pi bond here, and then you have a sigma bond here, and you got a pi bond here. You have a sigma bond here, right? So that conjugation adds stability. So it makes those double bonds way more stable than they would normally be, and way less reactive too. Right. So the fact that it's conjugated and it's super stable and it's an aromatic, right? So this is so something that's conjugated means you have a pattern of pi, sigma. Let me write it out. And then pi. Right. So all those p orbitals overlap. Right. So if I put p orbitals in here on each carbon in the ring, they all overlap. They form a 6-pi system, super stable. So you're not going to break that up. And then it's aromatic, which makes it even more stable. So if you have a choice between a pi bond that's just there and an actual aromatic ring, it's always going to be the pi bond that reacts. It's very, very, very difficult to get aromatic pi bonds to do anything without a catalyst present and really harsh conditions. Like you got to heat it up a lot, have a catalyst present, long reaction times, all that. So it's going to be here that reacts.
So you're going to have some type of carbonyl.
Yes. So what was the strategy I gave you all for thinking about ozonolysis? What do I need? What am I doing to that alkene?
You have to break it.
You're breaking it.
Breaking it in half, right? So I'm going to break this in half like this. And each side, right? You know, there's a carbon here. And there's also a carbon here. Each one of those carbons is going to become its own separate carbonyl. So when I do ozonolysis, that converts alkenes into carbonyls, right? So each one of those alkenes is going to become a carbonyl. So this will be an aldehyde on that side. And then the other one will be the same way. It's going to be an aldehyde. Come on, man. It's going to be an aldehyde on the other side. Like that. Right? So a pi bond, if I do ozonolysis on it, I'm going to crack it in half and I'm going to get 2 carbonyls out of it. Right, so these will be my 2 products. I'm just going to copy them.
So how do you know if it's gonna make a? I know they're both carbonyls, but how do you know if it's gonna make a ketone or if it's gonna make aldehyde?
It depends on what's bonded, right? Right here, you got hydrogens bonded. If there was some other group, like an alkyl group, like a CH3 or something like that, then it would be a ketone.
Okay.
So it's just looking at what's attached to carbon. That's how you tell the difference in an aldehyde and a ketone, right? You have a hydrogen on one side and a carbon or alkyl group on the other side. It's aldehyde. Got two alkyl groups on either side of a carbonyl, then it's a ketone. So that's going to be that for E, and then we did D also. I'll just put it in, and I'm going to abbreviate. I'll abbreviate that. All right. Any questions about any of these reactions that we've done with these alkynes? So what we've looked at with alkynes, we've looked at conversion of alkynes into enols, and we know that the enols don't stay, they're not stable, so they rearrange to give you the carbonyl, right? We talked about that, and then we've also talked about using the alkyne as a nucleophile by deprotonating the acetylide or the acetylene carbon, and then reacting it with some nucleophile that's primary. And then we talked about what we didn't talk about. Oh, yes, we did. Yes, we did. We talked about the secondary and tertiary reactions too, right? Where you take the acetylide anion and you treat it with react it with a secondary carbon or a tertiary carbon, and you get elimination. So we talked about that too. Yeah, and then reductions. We talked about alkyne reductions, where you can take alkyne and convert it to a cis alkene or a trans alkene, depending on the reagents. So those are the reactions we've talked about so far. All right, anybody have any questions about anything that we've discussed?
I have a question.
Go ahead.
For product C, it's not cis, right?
Say again.
For product C, it's not cis, right?
No, it can't be, because we talked about that, a triple bond. There's no cis or trans on a triple bond.
Okay.
Yeah. Yeah, so alkyne doesn't have any stereochemistry because it's linear, right? It's got a 180 degree bond angle. All right, other questions? I think that's the end of this handout, if I'm not mistaken. Yeah, that is. So when you take the, let me start recording. When you take the exam, you can turn this